Chapter 6 looks at the assumptions of multiple regression. Different books offer different sets of assumptions. The textbook that I used when I was in graduate school had something like 8, and Allison talks about 4 or 5 major assumptions, and then he talks about some other pieces that also need to be considered, but he doesn't consider those to be really central. And these assumptions are ways to ensure that the conclusions that we make about our multiple regression output is reliable, is robust, is valid. So these assumptions, we do violate them. We violate them quite often in the same way that we violate all kinds of other assumptions. But the inclusion of these assumptions provides us with a more robust outcome. Before we talk about these assumptions, Allison introduces a set of criteria for assessing any statistical technique and its validity and reliability. So first he talks about bias. So an estimation method is unbiased when there's no systematic tendency to produce estimates that are either too high or too low. Of course, the true value isn't available to us or possible to perfectly attain based on a sample. We know that we're always going to be underestimating or overestimating the true population value. But there's a difference between an unbiased estimate and a biased estimate. So we have to assume that if our method is unbiased, then our result is not systematically overestimating or underestimating the true parameter. We can also talk about efficiency. It's not enough for a method to be unbiased. We also need a method that is efficient. And he talks about it this way. He says, quote, efficiency has to do with how much variation there is around the true value. We measure that variation using the standard deviation. So efficient estimation methods have small standard errors. And we've talked before about sample size. So this is connected to that. Sample size matters. When we talked last week, we made the point several times that larger samples are typically better and are likely to be better estimates of the true population. Remember that as we took larger samples, the estimations that we had of the true population parameters approached the true value. So we moved from mean to approximating mu when we had large samples. So when we're dealing with small samples, we can't assume that same true estimation, or at least close to true estimation. So there are additional adjustments that we need to make. And we talked previously when we were talking about the central limit theorem and probability distributions that the larger our sample and the more samples we took, the more normal that distribution appeared, right? So it looked more like that normal curve. So with small samples, we cannot make that assumption, and we have to make some adjustments because the distribution of our variables will not follow the normal curve. So we have to make some adjustments to that. And then finally, he talks about probability sampling model. And this, in some textbooks, is included as one of the major assumptions of regression. So ordinary least squares, OLS, multiple regression, assumes a probability sample that everyone has an equal chance of being selected. Obviously, we can't do this perfectly, but using probability sampling allows us to assume that we are making a reasonable estimation of the population. So now let's start talking about some of those regression assumptions. The first one is linearity. So we assume that the dependent variable is a linear function with some random error, some random disturbance, right? Allison introduces the capital letter U as the disturbance term, which he uses to talk about random noise that may disturb the relationship between X and Y. Well, that random noise, that U, is the same thing as residual. It's all of the unexplained variation, right? So it's all the variables we haven't taken into account. It's all kinds of other things. So anything that is not considered in the model is considered disturbance or error or residual. So anything that's not included or incorporated into the model is unexplained variance. So it's the same term, but he uses the disturbance term and he uses the letter U to represent it, beginning in this chapter. The second assumption of regression is mean independence. So this assumption means that all of our x's, all of our independent variables, are unrelated to that random disturbance. Okay, so they're unrelated to the error. It's stronger, he says, to say that they're independent of the error, and it's weaker to say that they're uncorrelated with the error. But there is an assumption that the explained variance doesn't depend on the independent variables, that it's independent of the independent variables. So it's unrelated to the error term. So we assume that the mean also of the error is 0, that it's random, and that it balances itself out around the regression line. So the error above the regression and the error below the regression line are going to balance out. And so the total mean of the error is 0. Okay, so the mean of those deviations. This, he says, is the most critical assumption of all, because the violations to this can produce severe bias. And there's often no way to test for those violations. So what causes some of these problems? Well, when we omit influential independent variables. When the problem of reverse causation that we talked about last week. And problems with measurement error are all connected to this notion of the mean independence of error, of the disturbance terms. And again, there's no good way to test without having additional data. So we can't know whether measurement error is the problem. We don't know at the end that we didn't measure it well. We may not know that it's actually Y influencing X and not X influencing Y without some additional information. And we may not know that we've omitted influential variables until we include those variables or figure out which ones they might be. So there's no good way to test for and protect ourselves against problems with the second regression assumption, but it is an important one to consider. Regression assumption 3 is homoscedasticity. And that means the degree of random noise varies with the values of X. So what am I talking about? So it basically means that there isn't a pattern of error or residuals around the regression line, that it looks pretty scattered around it. So look at the image on the left here. So you can see that this is the regression line, and the scatter plot shows values all over the place around the regression line. So visually, we can look at this scatter plot and say, well, there's not really a patterning. But if we look at the one on the right, it appears to, and this is what many of the books talk about, it forms a cone around the regression line. So this is a pattern around the regression line where it's more tightly bound at low levels of X than it is at high levels of X. So there's more dispersion here at the higher levels of X and less dispersion here around the lower values of X. So this indicates heteroscedasticity. By itself, heteroscedasticity is not a problem, but it can increase inefficiency and result in a biased standard error value. We can address the standard error issue by selecting robust standard errors when we run our regression analysis, so it's sort of an option for us. We can address the inefficiency by using weighted least squares, which can become problematic. We can also transform the dependent variable in order to reduce heteroscedasticity. We talked about using logarithms to squish down the large number of responses and the effects of very large or small answers. We can use square roots sometimes to address this issue in the same way. And these are called variance stabilizing transformations. The problem with these is that it makes it more difficult to interpret, because when we square something or take the square root of something, it becomes difficult to interpret it in terms of the regression equation or what those resulting coefficients mean. The variance of the disturbances then should not be dependent on X. So the variance should be random. And that's what homoscedasticity is talking about. Same. Homo. That's the same root word. Hetero means different. The fourth regression assumption is one of uncorrelated disturbances. So if U is measured, if U is the measure of all the unmeasured variables that affect the dependent variable, then uncorrelated disturbances would mean that none of those variables that are excluded from the model are connected to those that are included in the model. Allison gives the example to illustrate what can happen of interviewing husbands and wives about satisfaction with their neighborhoods. So they're likely to give similar responses because they live in the same neighborhood, meaning that their responses would be highly correlated with each other. But the fact that you have two people answering about the same neighborhood isn't included as a variable in the equation. A more serious issue, he says, comes from repeated measures such as those that we find in longitudinal studies where the same individuals are asked the same or very similar questions repeatedly over the course of the study. And we would expect what someone says at time A to be pretty close to what they say at time B about the same thing. The consequences of correlated disturbances, particularly those unmeasured issues within the model, are efficiency and biased standard error estimates. Standard errors are almost always biased downward when we have correlated disturbances. And this tells us that the coefficients are less accurately measured than we think they are. So if we see really small standard errors than we would expect to, this might be a sign that something else is going on. So it implies that the test statistic would also be biased upward. So if the standard error is biased downward, then our actual test statistic is biased upward. And that means that we're likely to conclude that a relationship exists when it really doesn't. And it's difficult to assess uncorrelated disturbances because, again, we don't always know what isn't being measured, right? We have a hard time figuring out what's missing from our model. The fifth regression assumption is that there is a normal distribution of disturbances, that the error term is normally distributed across the line. So we talked about this normality assumption. It doesn't mean that all the variables in the equation have to be normally distributed, which is the common error that people have, is they believe that all of the variables in the equation have to be normally distributed. It doesn't. It just means that the error is normally distributed. Allison points out that this is the least important of the 5 assumptions for him. And again, sample size is important. The larger the sample, the more likely the resulting disturbance tests are normally distributed. We know that from what we've talked about earlier. We can check this assumption by calculating the residuals from the regression and plotting them to determine if they follow something like a normal distribution. We did that in the example when we ran SPSS, so we were checking that normal distribution of disturbances. Allison advises that when we have non-normal distributions of the error of the disturbances, that we use stricter p-values, particularly if we have smaller samples and we know that we're not getting normality. So we might choose to use 0.01 as our threshold instead of 0.05 because it's harder to reach that. So we can be more trusting in what we find if it reaches that 0.01 level. The overall impacts of these assumptions, and he talks about this on page 123 when he first introduces them before he talks about them individually, but he says assumptions 1 and 2 guarantee that the least squares estimates are unbiased estimates of the true population. And then when we add assumptions 3 and 4, we find that the least squares coefficient has small standard errors. And that's a good thing. And then combined with the other assumption, this final normality assumption implies that a t-table can be used to calculate p-values and confidence intervals. So together, this gives us a much more robust regression model. and we can be more trusting in our interpretation. Allison talks in the last section about how you'll find other textbooks with additional assumptions. One of them is that the X variables are fixed rather than random, and he doesn't really seem to think that that's much to worry about. And he says that it really exists just to simplify the algebra in the calculation of regression. But since the computer does it, it's not really that big of a deal. Other books incorporate an assumption that there's no perfect collinearity among the X variables, and he does include that in the assumptions, but he does spend the entire chapter talking about multicollinearity. So chapter 7 covers the issue of multicollinearity because it is so important when we are running our regression analysis and to the ability to successfully interpret and make claims about this causal and predictive relationship between our independent and our dependent variables.